Okay, so now that we found these omega and u, and we represented the analytical solution of u based on the Fourier series. So now I want to evaluate this over just one time step. So over one time step, we want to see how this function grows in time. And you see the omega k, t plus delta t, over omega k t is ck e to the minus d sigma k square t plus delta t over ck e to the minus d sigma k square t, and this equals to e to the minus d sigma k square delta t, and we define this as lambda k but analytical, meaning that this is also an amplification factor but an analytical amplification factor. So it is analytical amplification factor. And then, so this is the analytical amplification factor, but we already had the numerical amplification factors. So we define amplification ratio as RK, the ratio, is defined as lambda k of numerical, the numerical amplification factor, over lambda k analytical, the analytical amplification factor. So this is numerical amplification factor, which we found before. Amplification factor, and this one is the analytical one, which we showed it here, and the numerical one is this one, right? This lambda k that we defined here, where we just do it for the numerical method that we use. For example, this one is the amplification factor for this specific numerical approach. Okay, so now for stability, we require lambda k numerical to be smaller or equal than 1, and this is for the stability of the numerical approach. And for accuracy, we require lambda k numerical to be on the same order of lambda k analytical. And this means that RK should be on the order of 1. Okay, so this is the criteria for stability versus accuracy. And now I want to solve an example for this so you get more familiar how you can calculate this analytical and numerical amplification factor and also the accuracy criteria and amplification ratio. So the question asks, find stability criteria and amplification ratio of the following pure advection equation. And that is partial u over partial t plus v partial u over partial x equals to 0. So this is a advection equation, pure advection equation, and previous one we had a diffusion equation. So there is a difference here. And I want to do it with a forward in time approach, uin plus 1 minus uin, approximated with this over delta t plus v, backward in space, uin minus ui minus 1n over delta x equals to 0. So this is forward in time and backward in space. Okay. So let's see how we can do this. So I can rearrange this numerical approximation or as this. First thing I do, uin plus 1 equals to uin minus v delta t over delta x ui minus ui minus 1 n and then we write lambda k numerical by defining this. No, before that I want to do something. I want to define this as nu or current number. Some people even call it CFL number, current number, or CFL condition, and then rewrite it based on that. So uin plus 1 equals to uin 1 minus nu plus nu ui minus 1 n, and then we write lambda k numerical, the numerical amplification factor, as lambda k n plus 1 e to the, just based on this equation, e to the I sigma k j delta x equals to 1 minus nu lambda k to power n ei sigma k j delta x plus nu lambda k n e to the power I sigma k j minus 1 delta x and then I divide all of them by lambda k to power n ei sigma k j delta x, and this gives me lambda k, numerical lambda k, equals to 1 minus nu plus nu e to the minus I sigma k delta x, and this equals to, I can further simplify it, 1 minus nu plus nu, the definition of e to the I theta cosine sigma k delta x minus I sine sigma k delta x equals to 1 minus nu plus nu cosine sigma k delta x minus I nu sine sigma k delta x. Okay, so this is the numerical lambda or amplification factor, and now stability can be assessed by using this specific criteria that the lambda k of numerical lambda k should be smaller or equal to 1, and thus this means the absolute value of lambda k, which is going to be 1 minus nu plus nu cosine sigma k delta x to power 2 plus nu square sine square sigma k delta x should be smaller or equal to 1. And if you do some algebra, which I'm not gonna go through it, algebra, you will get finally to this equation with some trigonometric equations and other simplifications, that 2 nu 1 minus nu 2 sine square sigma k delta x over 2 should be smaller or equal to 0. And this means, because nu is v delta t over delta x, so delta t and delta x cannot be 0, and so that's positive, and this number is also positive, right? It's a square. So the only way that this can hold is that if 1 minus nu should be greater or equal to 0, and this means that nu should be smaller or equal to 1, and this is going to be the stability criteria for this pure advection equation, that is v delta t over delta x should be smaller or equal to 1. This is a very famous stability criteria in especially fluid flows, and that is called CFL number. And so this means that v delta t over delta x should be smaller than 1. In order for these approaches to be to have a stable numerical approximation. So the next thing that I want to do is I want to find now lambda k analytical, right? We found lambda k numerical, and now I want to find lambda k analytical. So for the analytical solution, we can represent u as a function of u here, as a function of Fourier series omega kt e to the I sigma k x. So partial u over partial t plus v partial u over partial x equals to 0. And this means d omega k over dt plus vi sigma k omega k times all of them times e to the I sigma k x should be 0. Okay, so d omega k, so this is the first derivative of that, and this is the second derivative with respect to x, right? So for all case this should be true. So d omega k over dt plus iv sigma k omega k t should be 0. And thus we can just integrate and simply solve this equation, which is going to give me ck e to the minus, by setting the initial condition for omega k at 0 is going to give me ck, like the previous example, e to the minus v sigma k t. Okay, and therefore lambda k analytical is gonna be omega k t plus delta t over omega k t, which is gonna be e to the minus iv sigma k delta t based on this. Okay, so as you see, interestingly, the absolute value of lambda k analytical is what? The absolute value of that is going to be 1. Right? And you can show it why, because this is going to be cosine x plus I sine, and I sine theta, so it's going to be cosine square plus sine square, which is going to be 1, right? So the absolute value of that is going to be 1. And so the numerical lambda k was what? We had it here. 1 minus nu plus something, so let me write it down here. 1 minus nu plus nu cosine sigma k delta x minus I nu sine sigma k delta x. And so Rk, the ratio, amplification ratio that we wanted to find, is defined as lambda k analytical and numerical over lambda k analytical, which is going to give me, by some simplification, it's going to give me 1 minus 4 nu 1 minus nu of sine square pi over Lk over delta x, and I'm going to define what is Lk, to power 1/2 over 1, right? Because that's the absolute value of the analytical k, whereas sigma k is 2 pi over lk. So lk is the relation between sigma k and lk is like that. And when nu is 1, right? That is v delta t over delta x is 1, then this ratio is gonna be, this is gonna be 0, right? So it's gonna also be 1 for all k, which is interesting, and that means that our solution is going to be completely accurate. The amplitude of that, actually, of course, not the phase. So I want to show you something briefly here. So if this is Lk over delta x, and this is the Rk, the amplification factor, so we know that 1 is the best one, right? It's where the numerical and analytical amplification factor converge to each other. So this means that the numerical approximation is behaving the best and is very consistent with the analytical solution. So let's see. If our nu is 1, okay, then no matter what our sigma k, or what is our k or lk delta x, or the discretization, the number of grids that we have, this is going to be always 1, right? So this is nu equals to 1. This is what we found here. But if nu is 0.5, 0.75, then this Rk is not necessarily that. Rk is going to be 0.5. You can calculate it. And then as you increase lambda k for Lk over delta x equals to 2, and as you increase lambda Lk over delta x, it converges to 1, right? So this is nu equal to 0.75. And why is that? Because Lk over delta x, if it goes to infinity, this means that this sign is going to go to 0. So this is going to become 0, right? So let me write it again here. Something is bad. 4 nu over 4 nu times 1 minus nu. 4 nu times 1 minus nu, right? So if Lk or delta x goes to infinity, this goes to 0, and thus the sign is also goes to 0. And so this term is going to become 0. And so Rk is going to be 1. So if nu is 0.5, then you will have something like this. So let me do it with another color. So this is nu equals to 0.5. So this nu is very important, this v delta t over delta x, because it not only is very important for stable, so these are all stable because nu is smaller or equal to 1, but it's also very important for the accuracy of the selected scheme. And as you see, if you nu is 1 for all k's, it's going to be very the amplitude is going to be very accurate. And for nu equals to 0.5 and 0.75, it depends on your grids, and it could be accurate or less accurate, highly accurate or less accurate. Okay, so it's very important issue that you need to consider. Okay, so this was the last lecture and of this course, and the last part of the course where we investigated the stability analysis for the finite difference approximations and finite in general all the numerical approximations. And we introduced a formal way of doing that by this Fourier analysis stability. And this has a lot of other things like we didn't cover, like analyzing also the phase of the solutions. We only investigated the amplitude of the solution. So the amplitude could be correct, but it could be that your phases are shifted a little bit for between the numerical and analytical solution. So this was just a brief overview for you to be familiar with this analysis, and if you're interested into that, you can take a more detailed look of that. So we started with this Fourier analysis for stability, where we showed that we can represent any function based on a Fourier series that is shown here, and in the complex form where we define ei theta as cosine theta plus I or minus sine theta. This can become like something like this: ck e to power I beta kx, right? And then we started with the using this for a stability criteria, and we solved it for we showed it for a diffusion problem. And then in this lecture, I tried to look at the accuracy versus stability, that this can also hold for analytical behavior, analytical solution. We can also show it with this Fourier series. And so then we defined an analytical amplification factor, which is shown here. And the numerical amplification factor, which is gained from the, obtained from the numerical scheme that we are using, and then we define this amplification factor as shown here. So for stability, we require that the numerical amplification factor lambda k, which is the ratio of the that Fourier representation in time at time n plus 1 or time n, which is a new time step over the old time step, should be smaller or equal to 1. Otherwise, if it is greater than 1, this means that our solutions is going to go higher, become higher and higher. It's like you add, you increase something by just by like 10% or 5%, and if it goes to infinity, it's just gonna go to infinity as well. It's gonna converge to infinity, and your solutions are gonna blow out. So that's why for the stability we require lambda k to be smaller or equal to 1. And for accuracy, we require that this numerical and analytical amplification factor to be on the same order. And that means that RK, the ratio of the amplification ratio, should be on the order of 1. And then I solved an example for finding stability criteria and RK of the following pure advection equation. So we first found the analytical, the numerical amplification factor, and we found that for the stability we need to, for this v delta t over delta x to be smaller than 1, which is the current number. And then we found the analytical lambda k, in which its absolute value is 1, and then we showed the amplification factor, the amplification ratio, and between the numerical and analytical one, and we found for nu equals to 1, RK is going to be 1, and for the other ones, we found this formula here. And this was kind of the representation of that, and its plot that is shown here. So based on the value of nu, you can have different stability and accuracy. And as you see, for all these nus, and they are all stable, but the accuracy can be different, right? So for one of them, the accuracy could be higher, for one of them, accuracy could be lower. So this is very important in order for you to consider when you are developing these numerical schemes, and when you want to assess which numerical scheme that you should use for solving your set of partial differential equations. Okay, thank you very much, everyone. Have a nice weekend.